Let's get started. So, hi everyone, welcome to our recurring Talk session. So, today we have the great pleasure to host Ali Hayoub, who is an assistant prof at Concordia University. So, before the talks start, a little reminder about the house rules. So, during the talk, that will last about 45 to 50 minutes. If you have any clarifications, questions, please raise your hand and feel free to ask them. But for more complex or open-ended question, please keep them for the second part of the talk, for the quick question answer session that will last for about 15 minutes. So without any further ado, Ali, the floor is yours for this presentation.
Perfect. All right. Thank you. Thanks a lot for inviting me here. I'm glad to be giving this talk. So I'll just dive right in. Yeah. So the title of my talk is Interactive Continual Learning for Long-Term Autonomy. Okay. So we have autonomous systems that are becoming a part of our lives in a variety of roles. A lot of it is going to be robots that I'll show here, but you probably have seen them, or autonomous vehicles and many other scenarios. So one of the things that we have in this for autonomous systems in the real world is that our real world is dynamic. So the systems will have to be dynamic to be able to adapt to that specific world dynamics itself. So things could change over time. Systems should adapt to that so that they can personalize to specific users to be able to assist them in specific tasks. So as a very simple example I could give you, because this is kind of an area I'm interested in terms of home robotics or domestic robots. So consider, like a very simple example. You have this robot or a collaborative robot that could be, supposed to help people in their home. And we train an object detector that works really well in one environment. You can detect every single one of these things actually very well. And I move it, I change the environment a little bit, I get different things, and it starts to break down. And this is actually quite, in this case, you would have to adapt this detector, train it on new data, or potentially a small amount of new data to be able to adapt to this environment. Same thing could be done for more about preferences. Like, for example, the user and the robot are interacting together, and then the question is, should one of them take the lead in the task, or the user or the robot? So each user could have their unique environments, could have their unique preferences, and over the long term, these could change over time. So how do we learn? Well, for me, the answer is through interaction with the users themselves. Where are the robots going to get that data from? The user is the best person to know whatever the change that just happened. They could potentially give it back. They could probably send it back to the industry or whatever, and the robot might have to retrain, or even it's a system. But that could be quite costly. It could be quite complex. So that's where my thing comes in. My research, essentially learning from non-expert human users about their unique environments and preferences to ensure long-term personalization or autonomy. So that's the goal. So long-term personalization to interactive continual learning to adapt to users' changing environments and needs. So for this, I would mainly focus on today two questions that I've focused on. There are a few others, but today for this task, I'll focus on these. So main first question is, how can we develop computational models, mainly machine learning models that can learn continually from limited data? And then second, how can we integrate these models into real-world systems for assistive applications? So this will be mainly robots that could actually use these continual learning models to be able to perform tasks in an environment. Okay, so for this, I combine machine learning and human-robot interaction. And this is kind of an overview of a lot of different works that have been in machine learning and robotics and human-robot interaction. I will mainly focus on works from machine learning and the intersection of learning and interaction, and a few works from here. And if you have any questions, I can go over other things as well. If you really are interested in HRI, I can talk about that too, but it won't be a part of my talk today. Okay, so the first will be on the first goal, of course, towards this longer-term autonomy is that we need to have models that can learn continually from limited amount of data. So let's start with the initial part of this, then I'll start diving in that, which is the continual learning problem itself. Now here I'll define a very specific form of continual learning problem from the machine learning literature. Maybe people here might already be familiar with it, or they already know other forms of continual learning, so we can discuss that if you have questions about that. So for me, I'll define continual learning as a machine learning model, say f of data, with parameters data trained on labeled data that is coming in different increments. So at t is the increment, and T could be the task itself. Each increment is a task, and task data could be, in this case, a simple object classification task. You get object classes fully labeled, you train the model, then new data comes in, you train the model, and basically your goal is that the model should be able to remember these past tasks while also learning new ones to be able to perform well on everything. In this specific case, specific setting, we are assuming that the overlap between these two tasks is 0. So, but in, of course, real world setting, it could not be. So we'll get to that. Okay, so a very naive approach to continual learning is that we just do fine tuning. We keep training our model on new data as it comes in. But the problem is that it could lead to catastrophic forgetting. So what is catastrophic forgetting? The model basically forgets all the prior knowledge whenever you learn something new. A very simple example of it is, I'll again give it, in this case, you train a classifier. There are 2 classes. This is a decision boundary, a linear classifier. Great. Now you get new data for 2 more classes here, and if you just train it on this data, you'll learn most likely something like this kind of a decision boundary, which will lead to forgetting of this classification task. So in very simple terms, that's the catastrophic forgetting. So how do we deal with it? One option is that we just keep replaying prior data. So as model gets new data, why don't we just store everything from before, keep replaying it, and train a model, and it won't suffer from forgetting. But of course, you could have issues, especially for robotics application or edge applications. You could have memory shortage. You could have data privacy issues, and more importantly, which I really focus on, is the longer training times. That in the real world environment, imagine a robot that has been trained on, I don't know, it's using a foundation model or something like that, a huge model that has been trained on thousands or millions or billions of samples. And now I get a new something that the model has never seen, and I want to train the model on that. Am I going to wait for many hours for it to train on that prior data so that I can learn something new? So that's why, to me, the longer training time is a bigger issue with replay, which I, again, will come to that later in the talk. Okay, so the very first thing I did, this is older work now. I won't go into detail too many of it, but the first thing we did was like, okay, why don't we just pre-train a model on ImageNet, and then we'll just do some online clustering. There's no forgetting here because we're freezing it. So just keep doing clustering here, keep the clusters separate for each class. There's no interference, no forgetting. And it actually did pretty well. I mean, you keep the cluster separate, and whenever you need to classify, you just find the distance of the new data point from the cluster centroid, and you're able to pretty easily predict. And we did, for example, tests on CFAR100 dataset or some other benchmark object datasets that are being used in continual learning literature. Also on robots that, this is like a Baxter robot that was interacting with some objects that we bought from Walmart or something. And we even had a data set that we released later on that are more real objects captured using the robot's camera while it was performing some manipulation tasks. So those were good. This is basically the approach CBCL. It did almost closer to or better than the baseline that were available at that time. But of course, that's because we have a pre-trained model, and we are not focusing on updating that representation at all. And the bigger issue here is that, let's just say we're not using object data sets, or objects that are different from the pre-trained ImageNet-based object data. What will happen then? So we need to figure out how to train this representation as well. So the next thing is that, okay, how do we do this? For my goal, what I did was okay, why don't we just do some generative replay? In this case, we train basically a generative model. This is, again, an older paper, so now we have other generative models. In this case, the goal was to train an autoencoder on data, then train a classifier model separately on the generated data and, the data you might get in each increment. So I'll go over quickly in this also. So the idea here was to do this neural style transfer based autoencoder. Again, these are older ideas, but I'll still quickly go over them. So the idea was to use neural style transfer as a part of the loss function to be able to train this autoencoder so that it is able to generate data that might be best for classification and later tasks. So here the goal, it wasn't really much to be able to preserve any other only the reconstructive loss knowledge, but also to be able to use this classifier that we're currently training already and use that as a content loss from the neural style transfer. Again, I can go into more detail if you have questions. So when you train the autoencoder, just simply store these feature vectors at the representation level, so memory storage will be low. And in the second phase, when we need to train, you just pass these feature vectors from the decoder, generate the data, replay only pseudo data, and of course your real data, that is you're getting at that increment, and you get the classifier. So generative rehearsal basically. And you can also do this with clusters, so it doesn't have to be only the feature vectors. We could even do clusters, and clusters of course can save memory, so you can discard the features, keep the clusters, and you can even save more memory. Okay, so again, it did quite well against mostly generative replay approaches, but on smaller data sets like CFAR10, ImageNet 50, SVHN. And still there were differences, bigger differences from the baseline. The baseline is the joint training model, which keeps replaying everything before. Okay, so, but the question what I'm focusing now these days with my students in my lab is going beyond this catastrophic forgetting. And there actually has been a lot of work in the past maybe 5, now it's 7, 8 years in this field, and a lot of focus is on catastrophic forgetting. So how do we deal with forgetting problem in continual learning? But the problem is it's not really the only challenge. We have plasticity, and this is what something I'll focus on right now, is that as you learn continually, you could lose plasticity in your model, which is essentially the loss of its ability to learn new data rather than forgetting prior data. Transferability, which is to be able to transfer prior knowledge so that you can actually learn something new, which is computationally efficient. Of course, if you keep replaying, there's basically almost no transferability because you're replaying the prior data to be able to preserve something, and it's really not helping or in learning anything new or be able to transfer those features from before. Okay, so like I said, I will talk about that. It's a pretty recent paper from a group in University of Alberta. They work on reinforcement learning. You probably already know this, maybe. So their paper showed, and they have actually been doing this work for a while, is that the models, neural network models, actually lose plasticity as you train them continually. And they actually showed a lot of different experiments with reinforcement learning. And this is actually this data set on CFAR100 data set. They did this example where you have this red line is the base deep learning model, which keeps replaying data and keeps retraining your model. And it actually has lower accuracy than a model that was probably trained from scratch, which is the top line over here. And they propose this continual backpropagation model, essentially to be able to reinitialize some parameters in your model as you continually train it so that you can preserve plasticity. We actually did analysis pretty recently in a paper, is that focusing only on one aspect of continual learning usually leads to other aspects being completely ignored. So this is an example of the plasticity law example. So this is the original paper results reproduced. The problem is that they're replaying 100% of the prior data. So in this case, their focus is not on stability at all or forgetting. They're simply focusing on plasticity. And they're saying, as if you keep retraining 100% of the time prior data, you will lose plasticity. The problem is we are not going to be doing that because that's not our goal. Our goal is not to do 100% replay. Our goal is to actually do a little less replay or almost no replay in the perfect setting. So here's the thing, when we go to 75% replay, so the gap in accuracy reduces. And by the time you get to 25% replay, what I mean by 25% is that only 25% of prior data is being replayed and 100% of the new data. So in this case, now you have almost no accuracy gap between the baseline deep learning model and any proposed plasticity preserving models. I'm having trouble saying this word. Maybe I should come with something else for the next talk. Okay, so the goal that for us, another thing that I want to focus on is that the computational efficiency analysis of continual learning. And you can see like training time reduces very much, a lot when you reduce the amount of replay. And second, if you have models that are doing something more than normal backpropagation, they're usually going to incur some computational cost. So if that's the case, is it really helping with what we're trying to do especially for real world or more edge applications? And even there were actually examples from other papers that, even if you have like training on Twitter feed, is your model training faster than how quickly you're getting data from, let's say, Twitter or they can use any other example like that. Okay, so what we're doing then is that basically balancing plasticity, stability, and efficiency. And the main thing we notice from this analysis is that backpropagation is greedy. It will try to override prior information, leading to the loss of plasticity. It's basically is going to use everything that is available in the neural network, all the neurons that are available. With replay, backpropagation will saturate the network parameters, leading to the loss of plasticity. Without replay, and also replay is computationally expensive. And but how we can deal with it is parameter reinitialization. So basically, while you train your model, yes, yeah, go ahead.
Can you recall what plasticity is exactly?
Yeah, perfect. Okay, so plasticity. So let's just say you are training a model. I'll go back to the example right here. Okay, so let's just say I'm training a model, and I have these new classes, and these are old classes. Now, as I train my model on old and new data, this is the capacity of the model to be able to learn new data as it learns continually. So does it have the capacity to learn new data? And I think it would have been better. They don't have the results from the paper. Actually, we have them, but I don't have in the slides right now. Is that we can show like what is the accuracy of the model on new classes and old classes. So over there, you can see actually if you do full replay, old class accuracy basically stays pretty consistent. But the loss here is because the new class accuracy is actually decreasing because your model does not have the capacity to learn anything new. So as it keeps,
like the average accuracy is fine, but the accuracy in the new classes that are being
it's
trained on are like
lower and lower and lower. Yeah, because the reason here, of course, is because of the replay. Because your model is getting 100 or prior data, which is helping it keep those parameters fixed that were assigned to previous tasks. So this is why the idea was to then reinitialize some parameters while you train. So basically, like randomly reinitialize some low utility parameters, and then your model can potentially use them for I don't know, a new task. And this does help, for example. So in this case, this red line is the base deep learning that keeps retraining, and then the top, which is blue and gray together now, the blue line is the model that keeps reinitializing some parameters as you train continually.
And the accuracy of those graphs is the average accuracy.
Yeah, average mean class accuracy for all the tasks learned at that point. So, for example, if we're at task number 10, that's the accuracy for all the classes in 10 tasks. So, any other questions? Okay, great. So I will. Oh yeah. So I was just recapping some of the things. So yeah. So parameter reinitialization can mitigate this loss of plasticity, but of course at the expense of computational efficiency. And I think that's it. Those are all the points that I wanted to make. I think I wanted to actually write something else, but I think it's not there right now. These are pretty recent slides because we just submitted the paper. So okay, it's actually says right there. I'm not gonna mention the conference or anything. Yes, yeah. Sorry. Yeah, we could do that too. For LoRa, I'm actually not that familiar with it, but I know that they're using some kind of a low rank like adapter on top of something that is pre-trained. Most of the time, it's a foundation model, right? So I mean, yes, that's one way to do it. But then again, in my opinion, I think it could still hit a wall like the one with pre-trained models that I showed earlier. So instead of now having a pre-trained ImageNet, you can replace it with a foundation model, and it could work. I think that's still a viable solution. It's practical, but if you are going back to the foundations of that, actually retraining, and if the foundation model hits a wall, then what do we do then? Or the foundation model itself has to be retrained, what do we do then? Yeah, so that's where in this case, I'm going back to those particular fundamentals. Okay, any other questions? Okay, great. All right, so for this case, this is a very preliminary model, and we're actually still working on it. I'll give you just an idea what we're doing. So the goal here is that to avoid these greedy updates in any new increment for each layer in the neural network, we're only going to select a certain number of parameters that should be updated. So essentially, we're budgeting a certain number of neurons per task. So the network's still the same. This is not like, oh, you're expanding the network or you're adding more neurons. You're just keeping the same network, just not letting it use everything. So those neurons are going to get updated for that particular task. The rest of the neurons are going to be reinitialized every epoch. So they're basically being randomly reset. So kind of an example could be, let's say this is the neural network. Again, very simple. You have task that comes in. This is the first increment. So we're going to randomly assign k parameters to be updated for task t. That's it. These are the parameters that the network is going to be updating in the back propagation. And the rest of the parameters are going to stay randomly reset. And the reason to randomly resetting them is that, you know, the network does not get attached to a certain representation here. So randomly resetting means that even if you learn something else in the future, the output of the network should stay stable when you learn new tasks. Okay, so let's just say when you go to the next part, to avoid forgetting in any new increment for the neurons that were assigned to the prior task, we're basically going to constrain their updates. In this case, this R here, the parameter, we can set to 0. So basically freeze those parameters. If you have no replay, if you have some replay, we can let the network update them. That's it. Very simple. So in this case, for example, you have task 2 comes in. You're going to randomly assign k parameters to be updated for the new task, and then freeze the prior neurons. And of course, these could be constrained updates if you have some prior data available. If you don't, then you basically just freeze them. Like I said, it's still a preliminary model. There's actually a few updates that are going on right now, but the results are actually kind of interesting. This is on no replay of the same task of 100 with the CFAR 100. In this case, we're assuming the network has the capacity for 100 classes. So we are kind of using some Oracle knowledge that it has. Of course, we know CFAR 100 will have 100 classes. This is the model results here. This is the SBP, selective backpropagation model that are proposed. This is the replay model that completely retrains everything. And these are basically all the other models that we tried. There are actually at least, I think, 1, 2, 3, 4, 5, 6, 7, 8 or 9 that we tried that didn't use any replay and all suffer from forgetting. Now, of course, again, going back to the question that was that if you use pre-trained model or LoRa type thing, yes, you can preserve, and actually they would probably do better than what we're proposing right now. But of course, you have this pre-trained model over there and pre-trained knowledge available. But in this case, there is no pre-trained model. It's just simple, the idea that I proposed. Okay, and this is actually an example where we change the budget. So now we're assuming, okay, we don't use the Oracle knowledge of 100 classes. We assume that it might be learning 1,000 classes. So this is ResNet 18. ResNet 18 does pretty fine, like on an ImageNet data set. So we're assuming maybe it's an ImageNet data set. And even then, you can see that the loss in accuracy is actually not significant. It's, I think, only 1% lower at the end of the 120 tasks for the same data set. So showing that, you know, this parameter itself does not have too much of an effect. So in this case, what we're doing is 0.5% of the neurons are being assigned per task. In this case, there are 5% of the neurons that are being chosen for each task. Now, the next thing what I want to show is that, okay, what if we start with a bigger data set in the beginning? So in the first increment, we start with 50% of the 50% of the classes, and then the rest are basically the same. In this case, of course, the model is able to better generalize to newer tasks. It's actually able to transfer the knowledge better, showing here that the accuracy actually improves over time, and actually even show you the new accuracy. So this is the new accuracy of classes as it learns, and this is the old accuracy. There is some forgetting, but the new accuracy is where I want to show that it actually is able to stay pretty consistent. This is, by the way, the model that is catastrophically forgetting. So of course, it has almost 100% plasticity and 0% preservation of prior knowledge. So that's the trade-off. And I think that's where I will end this part of the talk. If you have any questions, I will otherwise move on to the next about this. Okay. Yeah.
How does it compare to like building maybe a small neural network per task and adding on the ways that
Yeah. So I did look into the student also is working on those experiments right now. So we did look into that. The thing is that the literature that has the dynamic expansion networks, they start with something big like this. They will start with ResNet 18, freeze it or expand further from that. Now we're trying to see like if we can start with something smaller and try to expand on that, but it's it's not going as well as we but I don't have the results yet right now. Compared to other models that do dynamically expand from ResNet 18 to something bigger, yeah, they do better, of course, because you have now bigger net. Yeah, so it's for a fairer comparison, we have to try to find something that will be, of course, using the similar number of parameters, and then try to see. And of course, the computational. So also to mention that the computational time to train this approach is basically almost the same as training a normal backpropagation. There's no additional cost to training this compared to other models. So, but I'll have those results hopefully in the paper. Okay, all right. Any other questions? Okay, all right. So for now, what I talked about was this specific continual learning scenario where we have these task boundaries. There's no overlap in tasks. And we're also assuming that there is unlimited supervision, which is actually a bigger issue I have with this is that you get new data, you're assuming everything is fully supervised. These could be hundreds of thousands of samples, they're fully supervised. Now we're going back to the robotic scenario. If this is a user interacting with a robot, where is the supervision going to come from? Will the user be able to provide full supervision to hundreds of examples or thousands of examples in a single interaction or multiple interactions? So, like I said, real-world system might encounter a large amount of unlimited data, but limited human supervision. So what is the answer? The answer, it could be active learning, where you have models that can select, the most informative samples to be labeled, and then you curate the user only to, label those particular samples. And now, of course, in this case, if you do it continually without replay, you could have catastrophic forgetting, which is, of course, in the model itself, but also in this notion of uncertainty or notion of unknown that you might be using to actually find the new data, because as you go along, the unknown became known, and now what is unknown without any prior data available? So you have the forgetting issue. Okay, so for this, my work basically focused on this few-shot continual active learning problem, and I'll define that quickly here. The idea here that in each increment T, again, a continual model mostly gets unlabeled data, so there's no label available. We choose a few most informative samples to be labeled using an acquisition function, and then train on this labeled data coming from the oracle, in this case, the user. And note that the model itself is going to be helping the acquisition function, and the acquisition function is helping the model. So there's kind of a loop going on. Okay, so for this, the proposed model that I am going with is the continual learning part should be something similar to what I proposed earlier, CBCL model, very, very early, but it's GBCL with using Gaussian mixture models. And then for the acquisition function, I'll come back to that. So I'll go over each part of this. Again, this one, we are using a feature extractor, pre-trained feature extractor, just to go back to this, because this was very first work of its kind. So we didn't want to take risks on this representation part of it. And we also, when I show you the experimental setup, we are actually going to use only one sample at a time to train this model. So performance would be pretty bad on that. Okay, so I'll go to first part of the model, which is the continual learning part, which is Gaussian mixture model based continual learning. So our assumption is that each class can be represented using a GMM. And as you get new data, that could be streaming data, basically update the GMM for that particular class. And as long as your GMM can be represented with something simple, keep updating that. And if it's not, then generate new distribution. So as an example, oh, this is my email. Okay, so as an example, let's say you start with something very simple. You have a lot of data. It can be represented with a single Gaussian distribution. Great, go with that. You get more data. We update it. And as long as data could be represented with that same distribution, we'll keep it simple. But as we get more data, we can generate more distributions, expand this GMM as we go along in the streaming learning scenario. So this is the model for GBCL. Now let's go to the classifier training. So in this case, we do have a classifier, which is the task the model has to be able to classify objects. To avoid forgetting here, we're simply sampling the GMM representations, the Gaussian distributions, to generate pseudo data and train the classifier. Again, this is a very small, like a single layer or two-layer classifier. So the training or even generating these samples does not take that long. So generating pseudo data from distributions, new data that is coming in from the oracle and the current increment, train the classifier, avoid forgetting. Okay, and this is an example of actually the pseudo data that is being generated. This is on MNIST data set, two classes that we chose. This is the original feature space for 11th 1,379 images for 2 different classes. These are the generated samples by sampling the Gaussian components, mixture component. This is with 4,000, 2,000, 1,200 mixture components. So even with a small number of mixture components, we are able to basically regenerate data that is looking mostly like the distribution that originally was there. Now, if we go all the way, collapse it all the way to one Gaussian distribution, of course, it's not going to look exactly like what the original distribution looks like. But if you have enough components, it can generate pretty well. Okay, so I'll go to the active learning part. In this case, the goal is to use the GMM representation to be able to guide the model to be able to choose anything new. Here, we're going to use the entropy-based sampling and viewpoint consistency. The entropy sampling is very old, pretty simple idea. The idea here is that, of course, you have a new data. Its probability to belong to any prior distribution is low. Its entropy is high. We're going to focus on getting the labels for those samples. The viewpoint consistency is actually more specific to robotics. And the idea here is that, and it's actually from a different paper, that when the robot can actually look at different views of the same object, we can actually pass it through the GMM to see what could be the label that would be generated. And this doesn't even have to be a correct label. Here, I'm just using actually the correct label, but in this case, it doesn't have to be a correct label. The only thing we care about is if there is consistency in the labeling of the object. And if there is inconsistency, which means the model is giving different labels for different views of the objects, potentially it's an unknown object, and the model should focus on learning that. So we're going to combine both of these using a small hyperparameter, the entropy and viewpoint consistency, to use as an acquisition function. So these are the first experiment we performed in the dataset, Core 50. This is used for continual object recognition for robotics tasks. The original dataset had 10 classes, 400 training videos. So we converted it into the streaming session where at each increment, we're going to sample randomly 5 objects and then giving the budget to the user, or in this case, the Oracle, to label only one of them. So it's at each increment, it's going to learn one object at a time. And essentially, you have 400 training sessions, or 400 training increments, and then testing on the test set that was provided with the data set. So these are the results. The model is actually doing, the red one is the GBCL model. It actually does basically almost the same as the baseline, which is the green baseline is the few shot learning baseline, which uses a pre-trained network and then keeps retraining on the prior data. So this green baseline is using everything before. The red one is what we're proposing. Had almost no forgetting, but of course, we should remember that this is because of the pre-trained network also available here. So the one thing I wanted to show also was that it took only 15 increments to be able to learn data for all 10 classes, which means like it only wasted almost 5 increments to be able to learn. And it could also be, we didn't check, it could be possible that it didn't even have that data for those 10 classes in some of those 5 increments, because we're randomly sampling the data. Okay, and then we did experiment on in the lab with this Pepper robot. We attached cameras to its hand, and now we actually had 240 objects in the lab, 60 test objects, all of them placed on different locations in the lab. And then we took the robot around, and it can actually look at the robot, the objects by moving its hand around using its camera. And then the results are actually very similar. This is the GBCL model again. I should have made it bigger, or maybe you can look at it bigger over here. So it actually does pretty similar to, again, the one we saw on Core 50 dataset, almost no difference, which was great. And again, you see that the total number of classes were 20 here, and it learned basically all 20 classes in the very first part of the learning. And one other thing is that the accuracy saturates as you go along, which does show, of course, now you're not really learning anything new because you're basically learning more objects for the 20 classes. So it's really not adding. So this is really interesting results for us, because showing that the model can help the robot to adapt pretty quickly to a new environment. And then, of course, then it can saturate based on any new data that's helpful. Okay, so one last thing that I want to go with this part is what if the environment contains irrelevant or out of distribution data? So right now, most active learning focuses on really, like learning unknown data that is available. But what if it has out of distribution data? What if the robot is in a home environment where the data is just not related to its task? Maybe it's supposed to only work in the kitchen, but now it has other available objects that are in the home that it could try to waste its budget on. So what do we do then? So in this case, for example, the goal that we're focusing on right now there's currently work going on, is the robots essentially must learn what to ask the users to learn about their preferences and needs. And this is kind of the traditional open set active learning scenario right now. There are actually only 2 or 3 papers that I found. So their goal here is that to be able to detect OOD classes, and if the data is OOD, if the data is not OOD, which is in the distribution, then you do the selection process, the same selection process that you saw in active learning, and then you annotate and do the classifier, train the classifier. For our case, what we notice is that in this case, what they're doing is that in the beginning, how will you determine if it's OOD or ID data? And most open set AL methods, what they do is they basically pre-train a model on a small amount of randomly selected ID and OOD data. So they know all the ID and OOD classes that should be available in the environment. But of course, in the real world, you might not know how many or which OOD classes are available. So of course, you need fully annotated data in the start, and you should have full information about the OOD classes. So what we're doing right now is basically using some LLMs. I won't go into detail of this particular, because I don't think I have a lot of time left. So I have one more thing to show. So that's why. So we're using LLMs basically to reason on the knowledge in the beginnings. And our experimental setup is basically, we're going to start with knowing what objects are ID. Not the data for that, just the labels for that. The rest of it, we let the LLM reason on it. What could be the OOD classes that it could encounter in the environment? So no bound on that, and basically continually adapt. So these are some preliminary results just to show you. I won't go into again details. So the red model is ours. The blue one is the state-of-the-art current OpenSet AL model. And you can see this is on the CPAR10 data set with 10 classes. And we're learning only one at a time in this case. So what we can see here is that just look at the accuracy gap in the beginning with just using the LLM reasoning just to be able to predict what potentially could be the open set classes. And of course, as we go along, the saturation will happen because it's active learning and the data set is saturating at the end. So, but the real difference we saw here was that here, and you have to note that the model, all the other models actually have the idea what ID and OOD classes could be in the environment. And in this case, our model does not have that any knowledge about OOD classes that could encounter. Again, I can answer questions or go into a little more detail because the work currently is going on. So I didn't want to provide you anything that's not going to work. So, okay, so I'll stop here. So for now, for this particular question, what I talked about is continual learning, mainly on some limited data, in some cases, a lot of data. But a lot of that was for object data sets, simple tasks, or at least data sets. But how do we integrate them into real world systems for practical tasks? And real world systems, we see that they don't just work with object classification. They could have a lot of multiple data streams. So it could be semantic reasoning. So for example, I will just give a quick short example. Let's say, imagine a robot that is supposed to make you tea. It needs to do object reasoning, which means what a teapot is, and then spatial reasoning, where can you find this teapot? Task reasoning, how to use this teapot to actually make tea. Of course, and then grasping the teapot from how to grasp that, and finally agent reasoning, how does the person actually like their tea? So there are a lot of different data streams. Now imagine all of them are dynamic. So everything is changing over time. That becomes a much more complicated continual learning problem also. So in this case, what we focus on is 3 different streams being dynamic. One is object reasoning, spatial reasoning, and task reasoning. For a domestic robot, I'll show you the architecture. So this is kind of the interactive continual learning architecture proposed for a fetch mobile manipulator robot. And I'll go quickly over the different aspects of the architecture. And so first part of this is perception. Perception is pretty much straightforward. We're just going to do object detection to be able to get object features, pass them to some feature extractor. In this case, could be a CNN or a transformer. Get the features for objects, and for spatial context, for example, if it's a kitchen or something like that, we're just going to get features through like a knowledge graph, pass it through, get some knowledge graph embeddings for that, or it could be now LLMs as well. This is a little older. Okay. The next part is, okay, how do we do this continual learning? So in this case, we have a short-term and a long-term memory module. The short-term memory module in this case just stores the raw feature data. So object features or the context features or even task features if you have those. And this data is really just the robot observing the environment over time. So any daily routines, you just keep storing the data in the memory. But then the process of consolidation is that as a robot has hit a certain limit for a particular object, particular context, we're just going to consolidate it through a continual learning setup. So in this case, we're using like our clustering model that I showed you earlier. So anytime a little bit of adaptive model because we're actually making it as a part of the network. So in this case, if it hits this threshold, we're going to train this model, cluster it, store the centroids or Gaussian distributions, whatever, and then discard the feature representation themselves. So basically, short-term memory gets replaced with this, and then these clusters basically go into the long-term memory part. Okay, so what if the robot runs out of memory? This is actually the question that I feel like people haven't really answered or tried to answer in continual learning. Is that, and what if some of the objects get replaced over time? So we don't actually need to, keep replaying or keep remembering all the prior data because some data might not be needed at all. So in this case, what we're doing is a selective memory fading. So weights of the network that are associated with each task, there actually is a function of time in this case. And the equation here is basically based on when was the cluster or when was that weight parameter activated the last time. So if there is more delay, it will start to decay. This capital T here is actually a function of that. Again, I won't go into too much detail here, but I can answer questions if you have any. And this alpha here is controlling the decay rate. So for short-term memory, our decay we decided to be very high. Long-term, we decided to be a little lower. So this is kind of like the decay showing how it could. But the really interesting part here is that the short-term memory gets replaced very quickly. So it's it's because there could be short-term updates, we don't really need them, and they will get stored to go to long-term memory if they are very recent and very frequent. Okay. So that was more unsupervised learning. You could also have supervised learning, in which case the user could directly interact with the robot and teach it exactly what it needs to whenever. So in this example, I'm going to show now how this is again a very simple GUI, just to show like how a robot might be taught an object. So in this case, me showing the robot, fetch a robot. Okay, this is a book, and if it's graspable or not, I'm just going to show it a few views of the same object, usually 5 or 6 or something like that. And I can just start the session anytime I want, train the robot on this right then, and then go from there. Again, you're going to use the pre-trained model just to help with quicker processing and better performance. Okay, so for task learning, what we're going to do is I'm going to move. Again, I'm setting up the kitchen area here because that's what we had available. This was done during COVID time also. So in the lab environment, we set this kitchen environment. I'm taking the robot manually, showing it a different part of the kitchen, and then labeling it to be kitchen or not. Okay, the final thing is a task. So in this case, a task could be, I don't know, like a breakfast. That could be, I don't know, a glass of milk. In this case, I'm just going to say glass of milk. It's going to use the representation, store it in the memory. Okay, so how are we going to do reasoning? So in this case, reasoning is going to be done on semantic level, which will use the short-term and the long-term memory to be able to reason where could it find an object. So if it's an object fetching task, it's going to reason on that. And then, of course, it has to combine it with the actual metric map of the environments. In this case, the SLAM map where things are and connected with the semantic reasoning. So we're going to focus and prioritize short-term knowledge here whenever we're doing fetching tasks, because, of course, short-term memory is the latest that the robot saw in the environment. Okay, so now I'll show you this a quick, simple example. Again, this is all me. This is actually, you can see I'm wearing a mask in the lab right now over here. Okay, so this is the first case, which is fully supervised training. In this case, I'm training this model over time, over different days. And all of this was fully supervised. So there's no unsupervised learning happening in this part. And now I'm going to ask it to find me an object, which is an apple. It's going to go to the area, semantically reason, go to the area, try to then do local reasoning here. So it's trying to find apple. It does find it and localize it. So it has some other robotics modules with it. Again, I'm not going to go into those, the control module and all of that. And then, it's going to fetch it, bring it back. Great. It does well. Okay. Now let's do the same thing, but now I'm going to ask the robot to go find the apple, but now the apple location is changed. And it goes to the same location, which it has in the long-term memory, but of course it's going to do local reasoning. It's not going to find it. So now it's going to do start random search, and it's going to start to go into different parts of the environment just to see if it could find it. And it will eventually, when it goes to the area. Okay, so now it finds it. and eventually it's going to take it back. Great. So now let's see what happens if I try to ask it again. So now it's going to use the short-term memory, prioritize it, and it doesn't use the long-term memory, and goes, of course, it's going to pick up the apple and take it back. But the interesting part is now, if it keeps seeing this example here over time, it will get consolidated in the long-term memory that, now the location of the apple has changed, and it should go to that. Of course, there will be a probabilistic distribution that it still has some uncertainty if it's here or here. But as long as it keeps seeing more and more example, it will, shift that. But if it was a temporary change, it's great. Short-term memory will get discarded, and it'll still have that long-term location of the apple here. It can keep doing that. Okay, great. So final thing I want to show is that this was just one part of the architecture. There are other ways that we've adapted this architecture for other things. For example, in this case, we're doing collaborative object sorting tasks with the same robot, fully autonomous. So like more like an SM, like a industry environment where the human and the robot both sorting objects in like some environment. Also for memory visualization for people with disabilities. So the robot's memory could actually help, people that might have disabilities to be able to see the routines that they might have going through in their daily life, or for example, if they forgot to take medicine or something like that. And then finally, collaborative lifting tasks where actually the robot and the human actually can lift things together. Again, it has some control components with it, but again, the main aspect of the architecture here is always about personalization to each user, and to be able to adapt to that either within a single interaction or multiple interactions over a longer period of time. And then finally, we actually did do some experiments with real human experts coming in to teach our robot over like 5 different days to be, again, do this continual learning to see how this thing happened. But again, I won't go into those here right now, but if you have questions, I'll be happy to go to that. But to summarize everything, so towards my goal of continual learning to adapt to changing environments and needs, I've been working on machine learning parts, which is to develop machine learning models for continual learning. And of course, the robotic side of things, we're integrating these models into robots to be able to see if they can learn interactively with humans or even unsupervised over time. And my current and future research, again, from the domain aspect of it, what I'm interested in right now is, again, for assistive robotics settings and other personalized, any personalized, basically, IoT, healthcare, or any kind of areas. These are from the domain application aspect of that. But from the fundamental aspect, I am still, of course, interested in doing that kind of fundamental continual learning research. And with that, I will just thank all my collaborators, students. So the green ones are the ones that whose work is actually, I'm currently showing some of it. So they maybe you can remember these names that you probably will see again. And I'll just thank my funding agency. And with that, thank you for listening. And if you have any questions, please.
Yeah, you talked even a little bit getting to like memory constraints and things like that for robotics. And, models are getting a bit huge these days. So I guess, can you talk a little bit about is also part of the plan to have these systems running in on the robot as well? Like, what are the limitations in order to be able to do something like that?
Yeah. So in this case, our model was running. The example I showed you, this was all onboard computing. But you're right. If you're gonna use a big foundation model, it won't be easy to run it on the robot. It's just I mean the latency issues will also be there. I think the way to go, if we are gonna use a foundation model, we could do cloud, but again the latency could be an issue. Or we develop smaller foundation models for this particular edge applications.
So any ideas about ways to go about making a foundational model that's
personally, I don't do foundation model development myself. If I were to answer that question, I would just say let's do continual learning. So we start something small, and then we continually learn it in that environment. That would be my answer for that. Yeah, I mean, and then specifically the research that I showed you, the recent one, is really about that. It's like we start with something simple. Let's constrain the model a little bit and let it learn slowly over time. And it doesn't need to expand. It doesn't need to expand the model itself. It doesn't need to use any prior data, and we go with that. And again, we can also do forgetting, because we can replace prior knowledge which is not needed. Even for a foundation model, I would assume some knowledge might get outdated and it doesn't need it. So yeah, that would be my answer. But I haven't looked into developing foundation models yet myself. Yeah.
Okay, thank you.
Thank you very much. One of the main assumptions was like each task is like independent from the previous task. Have you ever tried to see the difference between your pipeline and like a soft continual learning where tasks are not like completely different from the previous one? Like
So
the evolution of the average accuracy that you showed, uh, depending on the number of tasks you're adding to the model. Have you ever tried to see what would happen if like the tasks are not completely different?
So you mean like the setting I showed in the active learning scenario where it's more streaming?
Yeah, when you showed like when you add a task,
Let me just go back to that.
and the average accuracy is
Mhm.
decreasing.
Okay, I see what you're. So you're talking about the first continual learning experiments that I was showing,
Yeah.
but not the active learning part.
Yeah.
Yeah. So that's the next step. We're gonna go towards that. It's like to go towards the streaming setting, and that's what I was saying. Like this is what we're doing right now is developing a newer model or adaptive version of that that we can actually do this with streaming data right as well. But if in the current case, the model that I showed you for continual learning is only for still where the tasks are more separated. Yes.
Okay.
Yeah. But we are working on the active learning part where it can actually do active learning streaming with that, and then also keep doing this continual learning while budgeting neurons. So combining both of the other ideas that I showed here for active learning and continual learning. Yeah.
Thanks for your talk. I want to know, did you consider a time as a constraint for your robots?
Could you please expand on that? Like timing means like the test, like the
For
latency.
example, the time that the robot can find objects correctly or understand it, just not the accuracy.
Okay, yes, I see what you're saying. So the amount of time it takes to find the object in the environment. Yeah, so, okay, I didn't show that here, but maybe from the video, you can kind of also see like when it does random search, it is taking more time to find that object. But once it has that, it's a lot less time. When it, of course, it's using that short-term memory or even long-term memory. When it knows the object location well, it just goes and able to find that pretty quickly. In terms of the model latency, that's related to the model itself. Like, so if it's a pre-trained model, it'll have this latency. Right now, we're just using the Resonant 18. We did try with mobile net or smaller nets. It does improve the latency on object detection part, like how quickly the robot can actually find the object when it is at the location. But again, it has the performance and the latency trade-off. Yeah.
Well, I also
I think
have
there was
one
someone.
question.
Yeah.
On the plot where you talk about plasticity, you're looking at the performance across tasks. So considering the previously learned task and the newly seen task, I was wondering if you tried to look at the distribution of performance and evolution of that performance for specific tasks. I mean, for each of those tasks.
Yeah. Also, that's why I try to show the. Maybe I can actually find those slides. Let me just see if I can. I don't know if people would see. Okay, maybe they'll see that. So this is actually the example of this. The original. This is the blue line here. Is the new accuracy, the new task accuracy. Okay. And this is the old task accuracy.
Okay.
So,
and orange is the previous task accuracy.
This is probably not the best figure. I think this is from my backup slides. Let me go to the original one. Where is it? Let's go to that. There we go. Okay, so this is for the case where you have 50 classes in the first increment. And this is the new accuracy as you learn 5 classes per increment. The black one is ours. The blue one is the model that will catastrophically forget. So of course it's going to have the best accuracy when it learns new tasks, but it has 0 accuracy when it for the old task.
By new accuracy, you mean
for the new classes.
classes.
Yes, exactly. So this is the accuracy for here 50 classes, 5 classes, 5 classes, 5 classes, 5 classes, 5 classes.
Okay.
And this is for the all the old ones. So here in this case, it would be, well, there's no old classes here, but here would be the accuracy for the past 50 classes, and then the past 55 classes and the past 60 classes, and then keep going.
So as you're learning new classes, you're forgetting about the previous one, and you're also your ability to fit the new classes is also decreasing. Okay.
Yeah, but at least there. Yes, which is the trade-off we're trying to still achieve. Is like, can we make it even better and make these curves all the way back up to the eventual base? But of course, when you let it be fully extreme level, you can see that you have full plasticity, but of course zero, zero stability. Yeah, so I think okay.
Just a question concerning the replay. So you had those curves with 25, 50%, and 75% replay. I was wondering, and I mean, it sounds like just the naive approach, that maybe you test when adding classes on the previous classes, you measure a drop in accuracy somewhere for certain classes, and then you only replay those. Like, is that something that people do? Like just simple heuristics, like we see a drop in accuracy of such, so we input such amount of data and replay only that amount of data. Do you know if that's being done? If that works?
Actually, I mean, I don't know, but I'm pretty sure someone has done it because there's like always every year there's like hundreds of paper in continual learning. But personally, I don't know any approach like that. But what I would assume, theoretically, again, assuming, what would happen is that when you do try to improve accuracy for some previous classes, and you only replay those classes, the other ones that you're not replaying, they will decrease, and you have to keep doing that for different classes at different increments.
Okay.
So yes, it could save the computational load, some computation load, but I would assume that the memory would still have to stay consistent because you have to store all the data. And I don't know about the performance, actually. I don't know what would happen. Yeah.
Okay, thanks.
When the robot does random search, do you think it can use it learns like association between objects to reduce the time it takes to randomly search for the object? So for example, if it learns that let's say apples are always placed next to bananas, then if the apple's location changes, then it can like use its long or short-term memory to reason about like where it can possibly find the new place?
Yes, it could do that. And actually, we have looked into that. There's actually even papers now on that. They use LLMs to be able to reason on this. Okay, where can I find this? And LLMs can reason and say, okay, you know what? All the snacks of like peanut butter, bread, or these kind of things can be in one area, and you can find them there. I think it works if your environment, you're thinking your human is very logical, and they're doing things in a very specific way. But I can tell, I mean, based on the experiment we did, even with real human participants, it's not like that. People don't have their homes set in those specific way. And this is why we let it be fully, like, yes, we can use it. We can do that. And when we don't have any other knowledge available of the user or the environment, we can use that semantic knowledge to be able to get our best guess. So yeah, you're right. So in the random search, we could probably use that. But once we have that knowledge about the environment, we want to focus on, we want to prioritize that. So my goal more is on the interactive aspect of it. So really like, focusing on that particular user, that particular environment, and personalizing to that.
You talked a bit about time regarding the fading memory. Do you also take time into account to make reasoning? I mean, like it's in the morning, I want a coffee, and is like the robot going to understand that it's the morning and it's going to be asked to make a coffee?
Personally, we haven't added that feature, but in a different work, we did do that. In that case, the goal was to make some breakfast options for the users, like any new breakfast options for the users. So in that case, we were considering time of the day also. But there are actually other works now that do add that feature, like time of the day as a part of the personalization aspect. So, but we haven't added it yet. Yeah. But there are many works now that do this, especially on LLM-based semantic reasoning. Yeah.
Any more question? Well, then let's thanks again, Ali, for this talk.
And I can end it. I can end the meeting here.